Okay, so I will start. So thank you so much for giving me the opportunity to give this lecture series at Waseda University. I will talk about fluid structure interaction, which is a topic that I've been working on for many years, on and off. It's a topic that has a lot of open problems still, which of course from a scientific point of view is very interesting. It's also a topic where you find many applications of the mathematical theory. Also from an application point of view, it's interesting. Okay, so what do we mean by fluid structure interaction? In general, we talk about fluid structure interaction whenever we have a mechanical system with a fluid and an elastic deformable solid or structure. I shall use these two words as synonyms, right? Solid and structure. So when we have a mechanical system with a fluid and an elastic structure, in which the fluid and the elastic structure interact with each other. In this case, we have a fluid structure interaction system. We have fluid structure interaction. So here's an illustration of a container with elastic walls. So the blue part, omega F, is a fluid, and this fluid is contained in a container with elastic walls. If you apply a force to the fluid, it will, of course, you will set it into motion, and whenever a fluid moves, certainly when it's a viscous fluid, it will exert a force upon its surroundings, in this case, the elastic walls. And of course, when we have a force exerted upon an elastic structure, the structure will deform. So we have, well, the fluid interacting with the elastic material, but when the walls are deforming, well, then the fluid domain changes, and therefore the flow changes or is influenced by this change. So we have interaction in both directions, fluid structure interaction. These kind of problems intrinsically have unknown geometries. So in this case, of course, the interface between the fluid and the structure is unknown, or equivalently, the fluid domain and the structure domain are unknowns. And the main goal when we investigate these kind of systems is to determine this unknown geometry. That's well, and the fluid flow. So the geometry, of course, is you determine the geometry by solving the equations governing the motion of the elastic material, because those equations will give you the deformation, and then you know the unknown geometry, and of course you're also interested maybe in properties of the fluid flow. Anyhow, so this is one example. Another example, which I also like, is the elastic plate clamped to a fluid-filled container. So again, the blue part in the second picture is a fluid. In this example, the fluid is contained in a container, and on top of the container we have a plate which is clamped onto the container, and if this plate is elastic, well, then we have again fluid structure interaction. When the fluid flows, the plate will deform and change and interact with the flow by changing the flow domain. Okay, fluid structure interaction. So what will I be talking about in the next hours, and of course also next week. Well, first of all, I would like to derive equations of motion describing fluid structure systems. This includes deriving equations of motion for the elastic part and for the viscous fluid part. And then, of course, for the whole system, the fully coupled fluid structure system. Okay, so deriving equations of motion obviously is something that the physicists do. I can speak for myself as a mathematician. I always found it not so clear how these equations with a set of equations coming from the physicist, and we try to solve these equations purely from a mathematical point of view. Now, this is what we do as mathematicians, but often it's, and in my view at least, it's quite useful to know details about the origin of our equations. When something is not, or something is very difficult to prove mathematically, one reason can often be that the physics is not right. So instead of sometimes fighting a mathematical equation which is not posed or which has a difficult structure, maybe it's easier to go to the equations, the physical equations, and have a look to see if maybe the reason for the difficulties lie in the model, and this can be quite useful for mathematicians to also include the physics. So I'm going to talk about a lot of physical principles that that are used to derive these equations of motion. Okay, so in my talk today, there will be a lot of physics, continuum mechanics. Okay, so once we have understood where our equations come from, obviously, as mathematicians, we want to solve them. I will start by looking at steady-state solutions to some fluid structure systems, steady-state, meaning time-independent solutions. And in order to do that, in order to obtain steady-state solutions, I will need LP estimates. It turns out that the steady-state equations of motion for fluid structure systems are elliptic. Both the elastic part in the steady-state case is an elliptic system, and the fluid system is elliptic. So we are coupling elliptic systems, which is, from a mathematical point of view, something we know how to do. I will show how to do it in an LP framework. And well, in order to do it in an LP framework, I need LP estimates. For the Lami system, the Lami system is the linearization of the elasticity equations that I will derive. And I need the LP estimates for the Stokes systems. Okay, so most of you have a background in fluid dynamics, so I will be assuming that you know the Stokes systems well. So I will be focusing on the Lami system. Now, the Stokes system is also very well described in literature. There are dozens of books and papers, textbooks even, on how to derive LP estimate, how to obtain a comprehensive function analytical framework for the Stokes system. So this I will not focus too much on. But the Lami system, which is the linearized elasticity equation, this you'll find it's hard to find in literature. There is one book which is the I guess you could consider it the Bible on elasticity equations, written by a French guy called Kyed. And that's the only textbook I could find, or textbook-like book I could find on the Lami system. So that's not it's not so popular, or there are not so many textbooks on this. So I will focus on this part. Okay, so once we have good framework for the Lami system, good framework for the Stokes system, then we can couple the two systems and obtain fluid structure interaction solutions to our fluid structure problems. Okay, so in the next step, I will move on to the unsteady case and look at time periodic solutions to fluid structure systems. Now, personally, I have and therefore also a lot of time periodic problems in the context of fluid structure interaction, and I will so I will talk about how to get time periodic solutions. Now, I kind of like to study time periodic solutions as the next step after steady state solutions, because time periodic solutions, in a certain sense, are the generalizations of steady state solutions. What do I mean by that? Well, one trivial time periodic solution, sorry, is the steady state solution, right? So I will come back to this issue. So one can think of time periodic solutions as generalization of steady states. Okay, the approach towards time periodic solutions is basically the same. We need LP estimates. We need LP framework. First for the Stokes system. In this case, of course, when we include the time, we have parabolic Stokes system. Then I will do the same thing, derive LP estimates for the hyperbolic plate equations. Now, why do I suddenly take plate equations here instead of a more general elasticity system? Well, there are open problems. At the moment, it's not known how to couple a 3D Stokes system with a 3D with a 3D no, that's not true. A 3D Navier Stokes in the nonlinear case. There are certain problems when you couple three-dimensional Navier Stokes equations with three-dimensional elasticity equations. There is a mismatch of regularity between the parabolic Stokes equations and the hyperbolic elasticity equations. This mismatch, well, in the case of the plate equations, which are simpler than the fully 3D elasticity equations, there are ways to overcome this this problem of hyperbolic parabolic mismatch in regularity. One way to overcome the problem is if you introduce damping terms. So I will first do that. That's the simplest way to overcome it. But then I will also look at how in certain cases to get results even if you don't introduce damping. Okay, so I will focus here only on the plate equations because there are no results on, at least not to my knowledge, on the fully 3D coupled Navier-Stokes and the 3D elasticity equations. Okay, and at the end I will talk about initial value fluid structure systems, yeah, and that's the plan for the talk. So let me start with the equations of motion. So so what I'm going to do now is I'm going to derive the equations of motion for an elastic, a 3D elastic structure, and the equation of motion for a 3D viscous fluid, and then couple these equations in an appropriate manner. So we use continuum mechanics. So we assume that both the fluid and the solid occupies a continuum. In a continuum, we differentiate between two types of forces. We have body forces that act on the volume in a given part of the continuum, and we have surface forces that act on as an example, gravity, that's a body force. Friction is a surface force. Okay, so when we have a body in a three-dimensional continuum, if we have a body force and a surface force, well, the body force and the surface forces are point forces. This means if you have a function representing a body force in your continuum, then the total force that this force will be exerting on a part here denoted by W of your continuum, you obtain by integrating your point force or density force function, and the same with the surface force. Okay, so that's basic continuum mechanics. We need the Olearian velocity in our continuum. The Olearian velocity, I shall denote it by small v, is the velocity at time t of the particle at the position x. Okay, we denote by small x of capital X of t. So by, we can consider small, or we consider small x sometimes as a function of capital X and t, and this function denotes the position of the particle that at time t occupied position capital X. Okay, so if we look at the function x and differentiate it in time, obviously we get the velocity of the particle that at time t occupied the position capital X. Okay, and this velocity we can also express in terms of the Olearian velocity. So we have the identity that you see here on the screen. By the way, if I do like this, can you see that I'm drawing on the screen?
Yeah.
Okay, good. Okay. So if we differentiate in our equation here, one more time in t, we get, well, with the chain rule, the identity that you see here. So this is just basically the chain rule. I use the gradient, the Nabla symbol, to denote the Jacobian of v, and this gives us for the acceleration of the point that at time t equals 0 was at position capital X. So this point is moving in our continuum, and the acceleration at time t we can express as grad v times v plus dt of v by the chain rule. Okay, so the notation grad v times v, I like this notation. It's a matrix times a vector, is usually written as v dot gradient v. Okay, so that's just a notational issue. Okay, I should use the classical notation from now on. Okay, we need to introduce mass. So the mass density we denote in a continuum. This means the mass of the particle that at time t is at position x. So this is an Olearian description of mass, and the Olearian description of mass we denote by rho. Okay, so also rho is the mass density. So in order to get the mass of a region in our continuum, we have to integrate the rho. Okay, and now we can write Newton's law in our Olearian description. This means in terms of the Olearian mass density rho and the Olearian velocity v, and we have here Newton's second law: mass times acceleration is equal to the force that acts upon our particle, and here F is a force. Okay. So conservation of mass is in short, when for any region, we have that the rate of change in mass equals the mass flowing into the region. So this we can nicely express in terms of the integrals you see here. The rate of change, ddt, of the total mass in the region V is equal to the total flow of mass per time unit into the region. So this is the total mass that flows through the boundary of our region V per time unit. Okay, so by the divergence theorem, we can convert the right-hand side, our surface integral, into a volume integral of divergence rho v, and then we can write our mass conservation equations as integral over v dt rho plus divergence rho v equal to 0. Okay, so if you have mass conservation, this mass conservation has to hold for any region W of your continuum. So we conclude that the function dt rho plus divergence rho v must vanish everywhere. And this, you see, is our first equation of motion, namely mass conservation. Okay, so that's just basic continuum mechanics, really. In the next step, we need stress tensors. Now we consider some region that is moving in our continuum, W of t. The motion of this region, so now we consider this virtual region as a body. Think of it as moving through our continuum. In this case, this body will influence its surroundings, and the surroundings will influence the body on the surface. Okay, so and this, of course, is due to intermolecular forces. So we need to express these types of forces, and we introduce surface force tau to express these intermolecular forces. Okay, so there's a very important theorem called Cushy's theorem, which states that the surface force due to intermolecular forces depends linearly on the normal vector on the surface of a region. So this theorem is derived from the principle of balance of total force and torque. So it's basic physics principles that tells us that that there is a symmetric tensor, 3x3 matrix, if you like, so that our surface force can be written as this tensor times the normal vector. This tensor is called Cushy stress tensor. So whenever we have a continuum, be it a fluid or an elastic structure, we can express the forces, the intermolecular forces that act on a moving region as a surface integral of the Cushy stress tensor times the normal component of the region. Okay, so that's the basic notion I need from continuum mechanics in order to go to the next step. Well, not quite. I just write Newton's law in a continuum, which we have all the ingredients to do at the moment. Let's consider some virtual region in our continuum, and and writes Newton's second law. So mass times acceleration is equal to the force, a total force that acts upon this region. So here on the left-hand side, we have our mass times acceleration density, integrate over W, so we get the total mass times acceleration, the total derivative of the linear momentum in on the left-hand side, and the total force on the right-hand side, our intermolecular forces expressed in terms of the Cushy the tensor, and some external body force here. Okay, again, we apply the Divergence Theorem to convert the surface integral into a volume integral, and we end up with Newton's second law in a continuum. Okay, so that's the basic stuff we need from continuum mechanics. So now I go to a viscous fluid, and I'll do this quite quickly because you probably know, maybe even better than me, how to derive the Navier-Stokes equations. Now we start with the intrinsic property of a fluid, that it has a pressure, or said expressed in another way, whenever the fluid is at rest, the intermolecular forces acting on the fluid is given by a pressure. So the Cauchy stress tensor in the fluid in the rest state just takes the simple form T equal to pressure function times the identity tensor. And we call this pressure function just the pressure or the hydrostatic pressure. Okay, so in case of a fluid in motion, additional intermolecular shear forces will act on the fluid, and to model these additional shear forces, we have to add we have to add the tensor here Ts to include the shear forces. Okay, so again, now we have to do some assumptions, and the assumptions, the main assumption that we do is to say that our shear stress tensor depends linearly on the gradient of V. Actually, by Cushy's theorem, the shear stress tensor must be symmetric. The whole stress tensor must be symmetric. So the stress tensor will depend on the symmetric part of gradient V, in fact. But the important thing is that we make the assumption now that the shear stress depends only linearly on the symmetric part of the gradient of V. I should have written here. Okay. Another assumption that we use is the assumption that the fluid is isotropic. So the stress tensor, the shear stress in particular, must be invariant under rotation. And well, so these two assumptions leads to this expression here for the shear stress. Okay, so this is our shear stress in a so-called Newtonian fluid, and Newtonian denotes a fluid in which we have derived the equation based on this assumption here. Not all real life fluids are Newtonian. If you think on, for example, ketchup or blood, you have examples of non-Newtonian fluids where you cannot make this assumption to get a reasonable model. So we have to realize that well, we are working only with a subset of the real life fluids when we make this assumption. Anyhow, so this is the stress tensor, Now I'm going to talk only about incompressible fluids, that is fluids in which the mass density is constant. This assumption is, of course, an assumption we make in order to get simplified mathematical equations. But in fact, the question is if this assumption in the context of fluid structure interaction really is helpful, or maybe this assumption is causes more problem down the road when we look for solutions to a system. On the first, when you make this assumption, density is constant, then certainly your equations just optically become more simple. But there is, as I said before, and I will come back to this point, there is open problem when you couple a parabolic fluid equation with a hyperbolic elasticity equation, and maybe this mismatch of regularity is down to our incompressibility condition. Okay, so now I'm going off on a tangent here in the beginning. I will come back to this point. Anyway, so as we often do in fluid dynamics, we focus on incompressible fluids by considering density constant, and in this case, the mass, the conservation of mass condition reduces to the solenoid, so the condition that our velocity field V is divergence free or solenoidal, and in this case our shear stress reduces to a constant times the symmetric part of the gradient of V, and we end up with the stress tensor you see here. Divergence of the stress tensor is a constant mu Laplace V minus gradient of P. The mu is a constant, which we call the viscosity constant, and terminology, I will refer to an incompressible fluid as a liquid. Okay, so collecting the equations for conservation of mass and Newton's law, so we arrive at the following equation of motion for an incompressible Newtonian viscous fluid. So rho times the Eulerian acceleration, which is given by dTv plus v dot grad v, is equal to divergence of our Cauchy stress tensor, which is given by the expression mu Laplace v minus gradient p plus whatever external body force F you may have in your system. So that's the Newton's second law. That's conservation of linear momentum, essentially. And we also include the conservation of mass. And from these two conservation laws, we obtain the equations of motion for a Newtonian viscous fluid. Okay, so these are the Navier-Stokes equations and the incompressible Navier-Stokes equations. And I will now move on to the elastic materials. And now I want to derive equations of motion on elastic material. So again, we know that we basically have to determine a Cauchy stress tensor, because once we have the Cauchy stress tensor, well, then we have via Newton's law, the conservation of linear momentum, and an equation of motion for our material. Okay, so in order to determine the Cauchy stress tensor for an elastic material, we need to mathematically describe our elastic material. This, in order to do this, we need a reference configuration of the material. So we need to know what the material looks like in an undeformed state. So it's actually important that the reference configuration that we consider is an undeformed state of the elastic material. Okay, so we need this information to describe or to derive a Cauchy stress tensor. Okay, so I'll use omega as an undeformed reference configuration of my material. Now we assume that a surface force, Fs, and a body force act on the material. In this case, the material, well, it's deformable, so it will deform. And we describe the resulting deformation by a function capital Phi, which may depend on time. The interval you see here is a time interval. So we have function which takes our omega at any time t into a new deformed configuration of our elastic material. So we make some a priori assumptions on the deformation, namely that it's injective with respect to the spatial variable for fixed t, has a certain regularity, and that it's orientation preserving. Okay, so we use these assumptions when we derive the equations of motion. Obviously, when we then later solve the equations of motion, we have to go back. We really should go back and check if the solution that we find, which will be the deformation, of course, if this solution satisfies the assumptions we have used to derive the equations of motion in the first place. This is something that we as mathematicians sometimes forget, but we really should do this step more often to know if the mathematical solutions are actually physically reasonable. Okay, so of course these types of deformations these assumptions on the deformation are not always met, also not in real life. One example of this is if you have self-contact. So if you have an elastic body which deforms in such a way that 2 points on the surface which are in the reference configuration apart from each other if they meet. So if you make a violent deformation of some elastic body, well, certainly you will have self-contact, and in this case, these assumptions are not met. Self-contact problems are hard to solve because you can, or one of the reasons, because you cannot make these assumptions on a deformation. So, okay, so anyhow, so I will consider the simplest case where we have a well-behaved deformation. A small deformation will always be well behaved. A bit of terminology. My undeformed reference configuration I will refer to as the reference configuration. Sure enough, I used that word already. The deformed configuration I will call current configuration. So when we work with elastic models, we always have to distinguish between the two, the current configuration and the reference configuration. Okay, so now I need a little bit of mathematics to go ahead with the derivation of the equations of motion. I need a cofactor matrix. We call that the cofactor matrix is equal to the determinant of a matrix A times the inverse of the transposed. So the formula you see here. Okay, so this is an important formula for us, and one of the reasons why it's important, you see here in the next part here. Consider a domain. Here I put R. Okay, well, let's do Rn. Let's consider a domain B in Rn sufficiently regular, and a function or vector field capital Phi that satisfies the assumptions from before, in particular orientation preserving. So let n ref denote the outer normal on B. So I can make a drawing, of course. So we have here some B, and then some deformation of B. Phi of B, so that's the setting. And on the original, in the current configuration, we have a normal vector, which we call NCUR for in current. And here on in the deformed configuration, in the current the other way around. The current configuration is the deformed configuration. So obviously our normal vector in the deformed configuration, in the current configuration, we denote by n-cur, and the normal in the reference configuration by n-ref, obviously. Like this. Okay, it's a bit hard to write on the screen. Okay, so now the question: what is the how do I compute from the reference normal, the current normal, and this you see in the formula here. And to understand the formula down here for the relation between the current normal and the reference normal, well, you just have to look here in the middle. If you look on the, let's look on the, on the left-hand side here. So we have a scalar product of a, we have a, so we have a scalar product here of the cofactor matrix of gradient phi times the normal normal ref, so the normal in reference configuration, scalar product with a gradient of phi times xi, where xi is a vector in the tangent space, so it's orthogonal to n-ref. Okay, so you consider this a scalar product, and then you transpose the gradient of phi, bring it over on the left-hand side in the scalar product, and utilize the formula for the cofactor matrix, and then you get, well, you get a determinant, but then you get on the left-hand side of the scalar product, obviously just the reference normal, and on the right-hand side, you're left with the xi, the tangent vector, and these two are orthogonal to each other, so that is 0. Okay, so this means that when you multiply the normal in the reference configuration with the cofactor of the gradient phi, then you get a vector which is orthogonal to the tangent space of the current configuration surface. So, well, obviously, this means it's directed along the current configuration. So now I overdid it with my pen here. For some reason, I cannot write anymore. Anyhow, so so this gives you the formula below. So cofactor matrix gradient phi times n-ref is a vector which is directed along n current. So if you normalize it, well, then you get the normal vector in the current configuration, and you obtain this relation between current configuration and reference configuration normal. So we will be using this quite a lot. Okay, so the next mathematical identity I need to proceed with the derivation of my equation of motion is the Piola identity. The Piola identity simply states for any C2 vector field phi, that divergence of the cofactor matrix of gradient phi is 0. Okay, and also I need the change of coordinate formula above from differential geometry. Just a second, I just want to test what has happened. Ah, now I know what has happened. This is the pen has no power. So I have to recharge it, and then in a few moments I can use my pen again. Okay, sorry about that. Okay, so now the Piola density. So this is actually a crucial identity. Without this identity, we would have also in the steady state case also a mismatch of regularity, but in the steady state case, the Piola identity saves us. So I want to show a very simple proof. The proof is based on the change of coordinates formula you see above. So if you integrate divergence of the cofactor matrix gradient phi over some subdomain B, and well, then by the Gaussian theorem, you can rewrite this integral as a boundary integral of the cofactor matrix of gradient phi times the normal on your okay, this is a ball, so let's, I don't know why I took a ball here. This could be any domain in the current configuration. Okay, but now we change form, we change coordinates, go from the current configuration into, so the surface of our current configuration ball into the surface of the deformed ball using the change of a coordinate formula above. And well, then if we recall the relation between the reference normal and the current normal, then you obtain just after the change of coordinate formula, just the integral over the deformed boundary of phi b of the normal in the current configuration. And again, by the Gaussian theorem, this is equal to the volume integral of phi of b of divergence of the constant vector. So this is 0. Okay, so and the ball here was arbitrary, so divergence of covector of gradient phi must be 0. Okay, I'm cheating a little bit here because in order for the cofactor matrix to be well defined, we need a vector field. Well, not to be well defined, but in order to use the formula from the previous page, we need the gradient of phi to be invertible, so non-singular. If but with some approximation argument, you can actually show this for even in the case when the gradient of phi is non-singular. Anyhow, so that was just because the Piola density is so important. I wanted to show you that it's basically just a corollary to the change of coordinate formula we know from differential geometry. Sorry, excuse me. Okay, so the Cushy stress tensor is canonically expressed in the current configuration of the medium, obviously, right? Because, well, the Cauchy stress tensor tells us is an expression of the intermolecular forces. So obviously it's expressed canonically in the current configuration. When we work with deformable materials, this is a problem for the mathematical investigations, and the current configuration is, well, it's an unknown. We don't know about the deformation. That's what we usually want to find out, how an elastic material deforms. So, well, if we don't know the deformation at the outset, well, then we don't know the Cauchy stress tensor at the outset, and so how are we going to get equations of motion? So that's the problem I'm describing here. Of course, there's a solution to this problem, and the solution is to transform the Cauchy stress tensor to the reference configuration, and we do this by introducing the first Piola Kirchhoff stress tensor, and we denote this stress tensor by sigma. Now sigma is a function on the current on the reference configuration, which I've denoted by omega. And as you see, it's simply a, well, it's we define the first Piola Kirchhoff stress tensor as the determinant of gradient phi multiplied with the Cushy the Cauchy stress tensor T, what do you say, put together, composed, no, concatenated with, no, not the right word. The Cauchy stress tensor now I forget the simple word for the composition, of course, the composition of the Cauchy stress tensor and our deformation times the inverse of the transpose of gradient phi. So, of course, if you recall the identity of the cofactor matrix, we can recognize this formula. The first Piola stress tensor as the Cauchy stress tensor times the cofactor matrix of gradient phi. Okay, so so this is obviously well, that's just a different definition. Why do we need this definition? Well, one of the justifications for introducing this Piola stress tensor is, well, the first, of course, now we have a tensor defined on the reference configuration, and we have a tensor which preserves the divergent structure of the original tensor. By that I mean that the identity you see here, divergence of Piola-Kirchhoff sigma, is equal to determinant of gradient phi, the deformation, times divergence of the Cushy stress tensor, composition with the deformation. Okay, so in particular, if the whenever the Cushy stress is the divergence of the Cushy stress is 0, then the divergence of the Piola-Kirchhoff is 0, and otherwise you have this the factor which you see here, determinant of gradient phi. Okay, so when we multiply a stress tensor with a normal vector, we obtain the so-called normal stress at a surface boundary point. And if we often we want to know what's the connection between the virtual or the surface stress in the reference configuration given by the Piola-Kirchhoff stress tensor sigma times n ref, and the normal stress in the current configuration, which is also the physical normal stress, Cushy stress tensor times n cur. And here you see the relationship, and this is just just plugging in the formula you saw before from the formula from the relation between n ref and n cur. So then we get this connection here. Okay, so we introduce now what is called a reference density, of course motivated by the previous formula, which is just the determinant of gradient phi times the current configuration density. So in physical terms, this reference configuration, this reference density is actually it's the physical mass in the reference configuration. More specifically, if you look at some region W in the current configuration, and you look at the deformation of this region, phi of V, and you ask what is the mass of phi of V? Well, that's obviously the integral of the current configuration density. Now you can change coordinates, and of course by change of coordinates you get the Jacobian determinant of gradient phi in your integral, and here you see that after the change of coordinate we are just integrating over the reference density, so we get that the mass of the deformed phi of V, the deformed region, is equal to the mass of the region itself. So the reference density I have defined like this is the physical density. Okay, so when we go between, when we transform our equations between reference configuration and current configurations, we always have to also transform the outer forces. So whenever we have a outer force, which is physically a force in the current configuration, well, when we transform our mathematical equations, we have to, of course, take into consideration that also this force has to be transformed from the current to the reference configuration, and therefore we introduce a reference force, FB ref, and a reference surface force, which are defined as you see here. And of course, these forces are not real physical forces. They are the result of transforming the physical forces in this way you see here into the reference configuration. They're called virtual forces. Okay, so the real forces are called applied forces. Virtual forces and applied forces. Okay, Newton's law in the reference configuration. We have mass times acceleration is equal to force, and here I use for Newton's law not the Olearian as I did before, but as I did when I expressed as I derived the Navier-Stokes equations, but rather the Lagrangian formulation, which is here a natural formulation because phi is the unknown, and of course the phi is the motion of gives me the motion of a point in the current configuration, right? So if I differentiate this motion 2 times, I get the acceleration multiplied by the well, now of course I have to be careful because the acceleration should be multiplied with the current density in order to get the physical mass times acceleration. Okay, so if I were to multiply my acceleration with the current configuration, I would get the divergence of the of this Cushy stress. But here you see in my formula, I don't have on the right-hand side divergence of Cushy stress, but rather divergence of the Piola stress. So that's why you see on the left-hand side, not rho cur, but rho ref. Okay. So this is, at the end of the day, what you are seeing here is the Newton's second law expressed in the reference configuration. Okay. So, now, why am I so focused on expressing my equations of motion in the reference configuration? Well, the reason is that the reference configuration is a known configuration, and that's the main reason, obviously. But I still have the problem that I don't know what is the Piola-Kirchhoff stress tensor, the sigma. This we now have to derive an expression, so-called constitutive equation, for our Piola-Kirchhoff stress tensor for our sigma. So now the first thing we do in order to obtain an expression for the Piola-Kirchhoff stress is to introduce the second Piola-Kirchhoff stress tensor, which is just equal to here denoted by capital sigma, which is gradient of phi inverse multiplied to the first Piola-Kirchhoff stress tensor. In this case, we get a symmetric tensor. Okay, so now let us start with the physical derivation of an elastic material. So a material goes elastic if the Cushy stress tensor is a function solely of x and the gradient of phi. Okay, so that's the intrinsic property of being elastic. If the material is assumed to be homogeneous, then it only depends on the Cushy stress tensor only depends on the gradient of phi, and we will consider homogeneous materials. Okay, so by definition, also the Piola-Kirchhoff stress tensor tensors will only depend on the gradient of phi. More precisely, a material is elastic and homogeneous if we can find so-called response functions, or if there are so-called response functions, so that we can express, for example, the Cushy stress tensor in terms of a response tensor t hat, depending only on the gradient of phi. Similarly, of course, we would in this case also have response functions for the first and second Piola-Kirchhoff stress tensor. Okay, so the sigma is the second Piola-Kirchhoff stress tensor. Okay, material frame indifference principle. So this principle states that any quantity of intrinsic nature must be independent of the particular orthogonal basis in which it is computed, right? So that's material frame indifference. So also a very basic physical principle. One can derive, it's not that easy, but you can derive from this principle that the response function in this case, or all response functions, only depend on gradient phi transpose times gradient phi, the so-called strain. So we introduced the strain, the Cushy green strain tensor, here denoted by C. And when we have from the material frame indifference principle, the response functions will only depend on the strain tensor. Okay, so obviously I'm not deriving this rigorously. I'm just stating which principles are responsible for which mathematical equations. Okay, another principle that we should invoke is the assumption that the material is isotropic. This means that the response of the material is independent of direction. We further assume, and this is important, that the reference configuration is stress-free. So in this case, the isotropy of the material implies that, our response functions are invariant with respect to rotations, as I've written here. Okay, so these are the assumptions that we use. Okay, so from these assumptions that I have mentioned here, we end up with a so-called Rivlin-Erickson material. Now, it can be shown, and this is, I guess, the theorem of Rivlin-Erickson, that the second Piola-Kirchhoff stress only depends on the principal invariance of the strain tensor. C itself and C squared. So the principal invariance of a matrix of order 3 are the 3 coefficients, by the way, of the characteristic polynomial. And here I stated this result is known as the Rivlin-Erickson theorem. Okay, so more specifically, the second Piola-Kirchhoff stress tensor of a Rivlin-Erickson material takes the form that you see here down below. So it's a response function which only depends on the strain C, and it depends on C in this very specific way in terms of coefficients of the polynomial c to the power 0, that's the identity, c to the power 1, c to the power 2. That is a polynomial with respect to c, and the coefficients depend on the 3 principal invariants of c. Okay, so that's a lot of stuff. I'm not going to go into the details with. This is the most, if you want to work with the most general type of elastic material, well, you have to use this at this second Piola-Kirchhoff stress tensor. Now we have a constitutive equation, at least, right? We have a stress tensor sigma, which depends or is expressed in terms of our unknown phi in a certain way. Obviously, one has to figure out what these coefficients are, and so in general, I guess there are, depending on the coefficients, different types of Rivlin-Erickson material. One simplified type is called the Solomon-Kirchhoff material, and in this case, the actually, I just said something that's not true. I said that the coefficients, the gamma, but those are not just any coefficients. Those are the, no, those are coefficients, sorry. Coefficients that depend on the principal invariance. Now, I take that back. That was true. Okay, anyway, so if we consider the so-called Salomon-Kirchhoff material, that's a special case of the Rievelin-Erickson material, in which where we have made some assumptions to simplify things. Basically, you see down here. It's a bit strange. You see the response function of the second Piola-Kirchhoff stress tensor for a Salomon-Kirchhoff material. So we have here specified how the constants depend on the principal invariance. So we have the we need to introduce the Green-Salomon strain tensor E, which is the difference between the strain C and the identity matrix times 1/2. Okay, so that's E. So in terms of E, we express the Salomon-Kirchhoff second Piola stress tensor. Now, this E is something we can relate to from a physical perspective, because it is a kind of a measure of how far away the strain is from a rigid motion. Because when the deformation is just a rigid motion, so not a real deformation, just a translation or rotation of your body. In this case, the strain C is the identity matrix, and the Green-Salomon strain, therefore, 0. So the Green-Salomon strain, in a certain way, and I know I'm doing a lot of hand waving here, but in a certain way, is a measure of the discrepancy between a given deformation and a rigid deformation. Okay. So that's how we relate to the E. Anyhow, so I told you about the physical principles that go into deriving a Rievelin-Erickson material. Now we make some simplifications on the coefficients in the Rievelin-Erickson response functions, and we end up with the response function you see down here, a constant lambda times the trace of the E, strain E, times the identity matrix plus 2 times mu times the E strain plus, and this is the small o notation, higher order terms in the Green-Salomon stress tensor. So the last bit here denotes higher order terms in E. Okay, so that's the Salomon-Kirchhoff material, and if we now disregard the higher order terms here, so make even one more simplifications, throw away higher order terms, then we arrive at the second order Piola, or then we arrive at a Salomon-Kirchhoff material, sorry. And if we express now the second order Piola-Kirchhoff stress tensor, we get a constitutive equation down here. So we have this is the first, sorry, it should be the first. No, I should write what I have written on my slide. Reintroducing the first Piola-Kirchhoff stress tensor, exactly. So the first Piola-Kirchhoff stress tensor takes the form you see down here. Okay, still a rather complicated expression, but as a simplification from the more general Rievelin-Erickson material. Okay, so typically we want to write these equations or the stress tensor in terms of the displacement vector field, which is the deformation minus the identity. And in this case, we get the following expression for the a Sormanov-Kirchhoff material, we get the following expression for the first Piola-Kirchhoff stress tensor of a Sormanov-Kirchhoff material. Right. So, and I summarize. So this expression was derived from material frame indifference. Frame indifference. We had isotropy of the material, and the material had to be homogeneous, and the reference configuration, remember in this equation, the U is the displacement with respect to the reference configuration. The reference configuration has to be stress-free. Okay, the constants appearing here are called Lami constants, and based on physical considerations, they have to be positive in order to have a physically meaningful material. Okay, so well, now we have our Cauchy. We have an expression for our first Piola-Kirchhoff stress tensor. So conservation of linear momentum can be written now fully in terms of the unknown displacement vector field U, and we have hereby obtained the equation of motion for 3D elastic Sormanov-Kirchhoff body B. Okay. Now we have equations of motion for the fluid, equations of motion for the structure. Now we want to couple the two. So we go back to our fluid structure system. We have a fluid part, structure part. We have an interface between the fluid and the structure, and we have outer boundaries. Think about our fluid in an elastic container. So for the fluid part, the blue part in the middle, we have our Navier-Stokes equation to govern its motion. For the elastic walls, the gray part, we have the Sormanov-Kirchhoff equations to govern their equations of motion. Now we just have to worry about or define how we model the interaction on the interface between the fluid and the structure. Okay, so these boundary conditions will now be written based on the principle of balance of forces. So we stay completely within Newtonian mechanics, and no slip boundary condition for the fluid. So this no slip boundary condition, you should probably know it already, states that a fluid, a particle always adheres to the boundary. This is completely unphysical, of course. Why would a fluid particle stick to the boundary? That doesn't make sense from a physical point of view. So one could argue that our no slip boundary condition in our Navier-Stokes equation are unphysical, but this is not quite true. In fact, you can argue that they are physically correct, such boundary conditions. How do you do that? Well, if you think about it, when we work mathematically with fluid equations, our boundaries, so our domains are smooth. At least it has some smoothness properties, right? But if you think about it, in a real physical on a real physical surface, a real physical surface is not smooth. If you zoom down to a molecular level, well, you have a rough surface. So our assumption that our surface is smooth to some extent is also not physical. Now, what you can show is that if you start out with a rough surface and with a physically reasonable boundary condition where the particles are allowed to slip on the boundary, then you can show that if you go to the limit from rough surface with slip boundary condition to and I know I'm hand waving here, but what does it mean to go from a limit? But if you somehow parameterize your roughness by an epsilon, and you consider the equations you get when you let epsilon tend to 0, then you end up with smooth. Obviously, the epsilon, the roughness parameter goes to 0. You end up with a smooth boundary, but importantly, you end up then with the no-slip boundary condition. So the no-slip boundary condition, although unphysical from at first sight, is actually a physically correct boundary condition if your boundary is smooth. I mean, this can be argued, shown, not obviously under a lot of assumptions. So you could maybe even make the argument if this is always the case, but at least it's not completely unphysical. I just wanted to make that point. Okay, so of course on the part of the boundary where the elastic material is clamped, we have no deformation, and this will also be reflected in a boundary condition. So let's start with the boundary condition on the fluid surface interface. We have a balance of forces, which we express in terms of our, well, Cushy stress tensor. So the force upon which the fluid exerts is the force that the fluid at a surface point exerts on the structure is given by TE in Fs, and this force is equal to, due to when we assume balance of forces, the force that is exerted by the structure on the fluid given by the structure Cushy stress tensor times the normal in this surface point. So that's balance of forces. Now, this is not always the case when you work in fluid structure problems, that you consider this balance of forces, fluid structure equations. You also have problems where surface tension is taken into consideration. In this case, the surface tension obviously also enters into the balance equation here, and then you have an additional force due to surface tension. So if you see the simplified boundary condition, this means that you do not model surface tension in any way. Okay, so the no-slip boundary condition states that, well, a particle in the fluid adheres, so doesn't slip on the boundary, so it adheres to the boundary. Now the boundary in our case, at least on the fluid structure boundary, is of course moving, because it's the boundary of a deformable material, and the velocity of the boundary point is given by dtu. What does it mean that a fluid particle adheres to the boundary? It means that it moves with exactly the same velocity as the boundary. So we end up with v, the Olearian velocity of the fluid, equals to dtu, the velocity of a particle on the boundary in the current configuration. So you need to compose the dtu with the phi inverse to go into the current configuration on the right hand side, because the v on the left hand side is the current configuration. Okay, so at the end of the day, we have when we make the assumption that our fluid is governed by the Navier-Stokes equations, and the elastic structure is governed by a Salmon-Kirchhoff equations. So we make the assumption that our fluid is a Navier-Stokes fluid or a Newtonian fluid, incompressible. So we end up with a liquid governed by the Navier-Stokes equations. And we assume that our elastic structure is governed by the Salmon-Kirchhoff equations of motion. I think we say just it's the Salmon-Kirchhoff material. That's how we express this assumption. So in this case, we end up in the case of the coupled system with this system that you see here. So in the first equation, we have In the first equation, we have the Navier-Stokes equations, of course, formulated in the current configuration, which depends on time. Okay, so we have, of course, the Navier-Stokes equations. We have two conservation laws, conservation of mass and conservation of linear momentum. Then we have the boundary condition on the no-slip boundary condition on the fluid structure interface, which is also moving. And we have then in the elastic material, we have the equations of motion based on the first Piola-Kirchhoff stress tensor sigma. So this is in the reference configuration. Now I use, I have made here the assumption that the reference configuration is the domain occupied by the material at time 0. Then it's a bit easier to write the equations. But in fact, mathematically, you don't need to make this assumption. Okay, and the final, finally, we have the balance of forces also on the fluid structure boundary. Here I've written the balance of forces in the reference configuration also. Of course, any of these equations you can write in, you can go between current configurations and reference configuration if you like. Okay, and on the outer boundary where the elastic material is clamped to the outer wall, we have no deformation. The deformation is or the displacement is 0. We don't have any displacement of the points there. Okay, so that's basically our fluid structure system, 3D elasticity coupled with Navier-Stokes equations. Our data, when we treat this problem as mathematicians, try to find a solution for given data. The data are the outer force in the fluid and the outer force in the elastic material. And the unknowns obviously are the motion of the fluid given by the velocity field and the pressure term and the deformation, or rather displacement u of the material. Okay, and here we have to, of course, to be aware that our fluid equation are written in an Olearian description, whereas our elasticity equations are written in a Lagrangian description. So at some point we have to make a transformation so that everything is written in the same description, and typically we would choose a reference configuration to rewrite everything in just one domain. Okay, we'll come back to that point. Okay, so that's all I wanted to say about derivation of the fluid. So I just wanted to give you an overview of the principles behind the derivation of the Navier-Stokes equations and the 3D elasticity equations, more specific, the Salmonov-Kirchhoff equations. Now I move on to the more mathematical part of my lecture, namely the quest for solutions. And I start with steady state, to look for steady state solutions, so time independent solutions. And in this case, well, our equations of motion in this stationary case looks like this. Yeah, so that's the equations from before with everything independent on time. So solutions to these problems are our equilibrium states, if you like, our steady states, stationary solutions. Okay, so how do we approach such a problem as mathematicians? Well, the traditional way, it's a highly nonlinear problem. Let me start by saying that. And the traditional way of showing existence of solution to a system of partial differential equations, nonlinear system of partial differential equations, is to linearize it and well, put all the linear terms on the left-hand side and all the nonlinear terms on the right-hand side, as I've done here in an abstract manner. Okay, so in this case, we can then identify a solution as a fixed point of the problem. Well, if you just imply the inverse of our linear operator, our linearized partial differential operator. If it's invertible in the setting you're working with, you can invert it, and then you can identify a solution as a fixed point of well, L inverse of n. So the composition of the inverse of our linear operator with the nonlinear operator. Okay, so in order for such an approach to work, obviously we need a framework of, well, we need Banach spaces, because in order to obtain fixed points, we need Banach spaces. Well, not completely true. Of course, there are fixed point theorems that require only metric spaces, but the best case scenario is that you have Banach spaces. That's usually when we do PDEs, the frameworks that we are aiming to find. Okay, and of course we need a framework in order to invert our linear operator, in which the linear operator is invertible, and the inverse should be continuous. Otherwise, it'll be difficult to find fixed points. So we need a setting in which our linear operator, a setting of Banach spaces in which our linear operator is a homeomorphism. So the goal at the outset is to find function spaces x and y such that the linear operator is a homeomorphism, and then we can look for fixed point afterwards. Okay, of course the spaces where the linear operator has to be homeomorphism also have to be chosen in such a way that the nonlinearity, the nonlinear mapping that we have on our right hand side, maps elements from the X space into the Y space, or otherwise this construction doesn't work. Okay, so what I'm saying here is, well, we need a setting of function spaces, a framework such that our linear partial differential equation after linearization is a homeomorphism, and a framework that conforms to the nonlinearity. So that all of this works. Okay, so linearized operator framework of Banach spaces such that the linearized operator is a homeomorphism. That's the first goal. And one of the first answer is Sobolev spaces, LP Sobolev spaces. Now, of course, why do we need so general LP Sobolev spaces? Why not restrict ourselves to the Hilbert space case where P is equal to 2? This has to do with the nonlinearity down here. So if we can establish a homeomorphism property in general LP Sobolev spaces, then then we have the freedom to look for a parameter P or exponent P, such that the nonlinear operator conforms to the setting. So that's why we need, and we really need to work in LP to solve these nonlinear problems. Okay, so we have, oh, I didn't even touch upon that point, but let me do it now. When we look at our fully coupled system, then we have two elliptic systems that are coupled together. If we linearize our Navier Stokes equations, then we get the Stokes equations. Well, in the steady state case, stationary case, the Stokes equation is an elliptic system, and the Solomonoff-Kirchhoff elasticity equations, if we linearize those, then we get a so-called Lami system, and the Lami system is also an elliptic system. So we have two elliptic systems. Now we need to establish Sobolev's or find a framework of Sobolev spaces such that both of these systems, so both of these elliptic systems are homeomorphisms. For that purpose, we need the theory of Aquin, Douglas, Nuremberg. So I write here in the title of this next chapter, ADN elliptic systems. ADN stands for Aquin, Douglas, Nuremberg elliptic systems. And when we talk about elliptic systems, then there are different ways to define ellipticity, I guess. and Aquin doctors Nuremberg, they found a class of elliptic systems for which they were able to show LP estimates, and those are the LP estimates that we need for our fluid structure systems. Okay, so without further ado, let me first introduce you to the theorem of Aquin doctors Nuremberg. I will use this theorem to establish, well, I can use the theorem for both operators, both the Stokes and the Laminate system. So it's kind of convenient tool. So let's use it. Okay, so Aquin doctors Nuremberg theory. Let us consider a bounded domain omega and an elliptic system consisting of differential operators I, j. So we have a system of differential operators, and they can be here general elliptic. Well, wait a minute. I'm not allowed to say elliptic before I define what it means to be elliptic. So we just have general matrices of differential operators. Well, we have one matrix A for our, let's call it the field equation. Yeah, so one system of differential equations in our domain omega, and then we have also a system of or a set of boundary conditions, and the boundary conditions are also given in terms of differential operators, in terms of boundary operators, B's. Okay, so let's see. I used this multi-index notation that you see down here with the multi-indices alpha, and we looked just as systems with real coefficients. Yeah, so that's a general system, a general boundary value, the general stationary boundary value problem. Okay, so now we need to define what it means to be elliptic, or rather what it means to be elliptic in the sense of Aquin doctors Nuremberg, because well, that's the type of systems that we can that are included in their theory. Okay, so actually this is quite actually it's quite complicated. We need, in order to define what it means to be elliptic, we need to introduce weights, and the weights, well, you see here n integers t1 to tn, n integers s1 to sn, and m integers r1 to rn. Now I have to tell you what is the capital N and the capital M here, because those are popping out of nowhere, I guess. So the capital N, this is the number of equations that we have in number of field equations, right? So it's the number of rows in our A matrix, and we have an n by n matrix, because the number of columns in the matrix is also n. So we have n equations with n unknowns. And the capital M, this is the number of boundary values that we have. Okay, so now we introduce the weights as here the T's and the S and the R's introduced in such a way that, well, let's start with this condition here. Alpha ij is bounded by the maximum of 0 and Si plus Tj. So what was alpha? Alpha ij is the stop with this here. A minute. The alpha ij, so this is the order of this is the order of the differentiable of the operator aij. Okay, so yeah, and beta hj is the order of the corresponding boundary differential operator bhj. Okay, so these weights have to well satisfy these conditions. At the outset, it's not really clear why, well, so I'll just leave it at that. It is what it is. Okay, so if these conditions are met, by the way, the S weights are we choose negative, and the T weights we choose a positive. Okay, so weights that satisfies the condition are called admissible weights for the system AB. Why do we need the weights? We need the weights in order to define the principal parts of A and B. So this is an interesting difference between systems and scalar equations. In systems, it's not clear what the principal part is. So if you just have a scalar equation, well, the principal part of your symbol is the derivative of highest order. Yeah, but here we have mixed, we have derivatives of mixed order. So if you think about a system, of course, we have, we go back. Here, well, each term in our differential, in our system of differential equations has, well, it has some order. Now, of course, you could go and say we just use the symbol or the highest order terms with respect to differentiability, but somehow that doesn't give you the correct definition of ellipticity. So you have to introduce these weights. So the weights are needed. Let's leave it at that to introduce what is called principal parts of A and B. Right, and you see here the principal part of the A operator is the other terms of where the order of derivatives is given as, well, here Si plus Tj. So the weights will determine what is what are our, in quotes, highest order derivatives, or principal, what goes into the principal part. Okay, so yeah, okay, so that's not really 100% clear when you just see it at the outset. Why? Just go back. Whenever I look at these weights, I think, okay, but there has to be some deeper meaning of these weights. But its funny thing is, you can choose the weights in different ways. There's no unique way to choose these weights. So I always leave, whenever I used Aquin-Doctor's Nuremberg theories, I'm always confused about these weights. How come you can choose different weights? And anyway, so let me give you the theorem before I give you the confusion. So we introduced an R, which is the maximum of the R weights, and we use the R here to assume sufficient regularity. And yeah, and now we define the setting of Sobolev spaces. So basically, the Sobolev spaces that you see are correspond to the order of our Sobolev spaces correspond to the weights we have chosen, right? So our operator A takes a function in or a vector in with components, or let's say it like this. So the differential operator A takes a vector with components in WR Tj plus KQ. So Sobolev space with exponent R plus Tj plus K. Okay, we fix the K is fixed, by the way. You can fix K to 0, so then it becomes a little bit more simple. So, but the Tj weights, they determine then the order of the Sobolev spaces for the for the unknowns, and the corresponding Sobolev spaces for the data are then determined by the S weights and the R weights for the data, the right-hand side of the field equation, and for the boundary values. Okay, so the weights determine the Sobolev spaces that we choose for our setting. Of course, you see here a trace space, and this trace space is of course chosen such that by the trace theorem we get a well-defined operator. In fact, these trace spaces are sharp, meaning that we can hope for a homeomorphism here. Okay, but yeah, so I have to move on, and I can return to these weights and my confusion about them. But let's define now what it means to be elliptic. An operator A is said to be elliptic if the determinant of the principal symbol. So if you replace the differential the differential operators with a psi, then you get the symbol of an operator. You know that stuff, I'm sure. And when the symbol, of course, is a matrix. In our case, here we have the symbol of the principal part. And remember, in order to define the principal part, we need the weights. So the principal matrix symbol, the determinant of this matrix has to be non-zero everywhere when we choose xi, which is non-zero. Okay, so that's kind of standard. So the definition of the principal part is kind of funny with the weights, but ellipticity essentially means that, or you can think of ellipticity in this way: if you are in the whole space and you can Fourier transform your equations, then ellipticity is then you have, after Fourier transform, of course, an equations with polynomials, and when you can invert these equations, just algebraically invert them, then you have ellipticity, and this, of course, is the condition that you see here. Okay, so in order to be elliptic in the sense of Aquin, Douglas, Nuremberg, we also need properness of our elliptic symbol. Our elliptic symbol, an elliptic symbol is said to be properly elliptic if the degree of the characteristic polynomial, the characteristic polynomial is just the determinant that you see up there, determinant of the principal symbol. If this characteristic polynomial has even degree, and for all, if you fix the x on the boundary, then you can construct, whenever you have two linear independent vectors, xi1 and xi2, then you can construct polynomials of this type here. Okay, and these polynomials that you get by considering symbols at points on the boundary in this way, they have to have exactly m roots with positive imaginary powers, and therefore also exactly m roots with negative imaginary powers. So we cannot have any roots, any real roots. They have to split, and they have to split evenly. Now, the good news is that this properness condition is automatically satisfied in dimension n above or equal to 3. So unless you are in two-dimensional, you work in two-dimensional problem, the properness is always given. Okay, now we come to the complementing boundary condition. And this is, okay, so this is really confusing or complicated condition. Let's have a look at it. A system AB with associated admissible weights is said to satisfy the complementing boundary condition if the if the A differentiable operator, so the field or differentiable operator, is properly elliptic. Okay, and here comes the funny part. So if for all, when you fix an x on the boundary, okay, so now you have a bound, look at a point on the boundary, and then you take here a psi in the tangent space on this point. Yeah, so the tangent space at x. Okay, so now you construct using your boundary symbols, or rather the principal part of the boundary symbols. You construct polynomials in this way down here. So so we fix the x, and then we consider, and we fix the psi, and then we fix an n, which is a normal component to the tangent space. Okay, the normal to the tangent space, and then we introduce a tau, which well, takes psi. Okay, so psi plus tau n is a path or a line in the normal direction. Okay, so depending on, so we can consider this as a polynomial in tau. Okay, then we get a number of polynomials. So we multiply these polynomials with the cofactor matrix of the principal symbol of A, also evaluated, symbol evaluated in psi plus tau n. Okay, then we get polynomials that denoted here by C. Okay, so these polynomials, they have to be linearly independent modulo the polynomial that you see here in yellow. So the tau h plus or tau 1, we denote all the roots of our characteristic polynomial by tau, and then we need for this condition just those roots with positive imaginary parts. It's horribly complicated. And then the linear factors corresponding to these roots with positive imaginary powers, okay, this is constitutes the polynomial, and we have to ensure linear independence of our C polynomials with modular this polynomial, which is the product of the linear factors. It's horribly complicated, and at the first glimpse, this seems impossible to actually verify in any reasonable way. In fact, this is quite difficult when you have symbols that are a little bit complicated to verify directly, which we won't do. But I also don't want to talk about this condition without showing it to you. And in fact, when you work, if you read the proof of Aquin, Douglas, Nuremberg, this is a quite long, complicated proof. The condition is quite natural, funny enough. This has to do with the way that you solve elliptic problems in the half space. So if you're in the half space, then you can employ the Fourier transform in tangential directions. That's why we here differentiate between tangential directions and normal direction. But if you're in a half space, then you cannot apply Fourier transform in the normal direction. So you end up, if you only do Fourier transform in the tangential directions, then you end up with an ordinary differential equation. Okay, if you have non-homogeneous boundary values, then you have to somehow lift these boundary values. And the lifting of the boundary values, there's a formula for this lifting, and these expressions you see here are the expressions that appear in these formulas. Okay, so that's just a little bit to give you the context. Of course, it's a terrible, horrible condition to actually have to verify for some system, and we will not do that. There are other ways to do to equivalent conditions. So let me quickly come to the equivalent conditions before we whenever I see this complementing conditions, I get yeah, slightly confused about the way it's or at least a little bit scared of actually having to get my hands dirty with the condition directly. Okay, so what does it mean to be elliptic in the sense of Aquin, Douglas, Nuremberg? Well, a system of differential operators matrix A and the and boundary operators B, system of boundary operators, is said to satisfy the complementing boundary that satisfies the complementary boundary condition, is said to be elliptic in the sense of Aquin, Douglas, Nuremberg, or the ADN elliptic. So the class of the systems that are ADN elliptic are is a class of systems. In fact, it's precisely the class of systems for which we can show an a priori estimate of the type you see down here. So down here we have our a solution U to our elliptic system, estimated in our framework of Sobolev spaces in terms of the data on the right-hand side and the boundary values in corresponding Sobolev spaces, plus a term lower order. So Aquin, Douglas, Nuremberg theorems in the elliptic case always have this lower order term on the right-hand side, and this the reason for this is that the theorem here is formulated for systems. It's formulated for systems on a bounded domain. So general bounded domain. So now the way you show these estimates is you localize. So there's a localization argument behind it. This means you flatten your boundary and then you apply estimates in half space estimates and whole space estimates. So, but since you're localizing, you always end up with terms of lower order on the right hand side. By the very nature of a localization argument. Now, if you can show uniqueness of your solutions, so if you can show that your system of your elliptic system, it has a trivial kernel, then the lower order term disappears by a compactness argument when the domain is bounded. Okay. So, Aquin, Douglas, Nuremberg. So these are the LP estimates that are so crucial to the fluid structure problems. And yeah, well, Aquin, Douglas, Nuremberg is the tool set that is typically used. At least that's the only theory that I could find in literature for elasticity equations relies on this Aquin, Douglas, Nuremberg stuff. So I thought I would show it to you today, and how to work with it. Now, I don't want to work with the complementing condition directly. So instead, I will use what is called the Lobachevsky-Shapiro condition. This is an equivalent condition to the complementing condition. Okay, and basically it says that if you consider your elliptic system in a half space case, yeah, so this, yeah, in a half space, then if you can show that there are no non-trivial solutions of the type you see here, so you have an oscillating term e to the power xi dot x minus x naught, x minus x naught. This is our so if let's see, so the half space that we're considering is this half space here. So it's say half space with origin in x naught, and the xi is yeah, here. So xi is normal to the normal direction. So this is in the tangential direction. Okay, so whenever you have a solution of the form U to the half space problem of the type you see down there with an oscillating term at times a function v that it decays exponentially, whenever you have a non-trivial solution of this form, then it has to be 0. Yeah, that was not formulated very well, because non-trivial solution means that it's not 0. As it says here, the condition states that if there are no non-trivial solutions of this form, so whenever you have a solution of this form, you have to show it's 0. In this case, the condition is met, and in this case, so the statement of the theorem, in this case, your elliptic operator, your elliptic system satisfies the complementing condition. Okay. This is a much nicer condition to verify. And again, I remember I told you that the complementing condition is in fact appears quite naturally when you read the proof, because it has to do with the half-space problem. And so it's natural that the Lobachevsky appearance is also a half-space problem, and it has to do conditions on the solutions that you get in the half-space case. Let's leave it at that, because otherwise I would have to go into the details of the Aquin-Nuremberg theory, and that's not the point of my lecture here. Now, one additional theorem that I like to use quite a lot, and it's the Theorem of Gamuna. It states that the following statements are equivalent. Your operator or boundary system of boundary value problems corresponding operator is elliptic in the sense of Aquin-Nuremberg. This statement is equivalent to the statement that for some Q and K, the operator is Fredholm. Now, Fredholm, obviously, in the setting of the LP Sobolev spaces, in which the Aquin-Nuremberg theorem was stated. Okay, but for some Q, okay. Okay, this is okay. So from 1 to 2, okay, that's nice. We know if it's elliptic, but not Nuremberg elliptic, then it's a Fredholm operator for some Q. But then from 2 to 3, it says that if it's a Fredholm for some Q, then it's a Fredholm for all Q. Yeah, we have equivalence here. You can also go from well, no, actually, you want to go from 2 to 3. If you can show that your operator is Fredholm for some Q, and you don't just choose any arbitrary Q here, you choose Q equal to 2, because then you are in the Sobolev space setting. If you can choose Sobolev space, you're in the Hilbert space setting in this case. So if you can show in the nicest case where Q is equal to 2 in the Hilbert space case, if in this case you can show that your operator is Fredholm, then it's Fredholm in any LQ setting. Now I am a little bit confused, because here it says Q, and I always use the letter P. I talk about LPs over the space. This is a typo. This should not be Q. This should be a P. So okay, I'll just reiterate. So the power of this theorem is that if you can show that your operator is Fredholm in the Hilbert space case, then it's Fredholm in any LP case, the any corresponding LP case. And Fredholm essentially is equivalent to elliptic in the sense of Aquin-Nuremberg. Okay, so I will be showing you now that this is, I will focus on this here in the last part of my lecture, on showing you how to use this very nice theorem to show that the elasticity equations are elliptic in the sense of Aquin-Nuremberg. And more than that, in fact, I will show that the Lami system is, or the corresponding operator is a homeomorphism. That's what we really need. Now, homeomorphism I have when I have Fredholm of index 0 and the kernel is trivial. This is equivalent to a homeomorphism. And okay, so now I show how we use these tool sets to do that. Okay, I have one small problem that I have to address before I dive into the Lami system, ellipticity of the Lami system. Now, the general theorem of Aquin-Nuremberg, we can just go back here, is stated in, let's go back, sorry about this, is stated like this, right? So, I have one system of boundary operators on the boundary. Obviously, that's how you would state a theorem in this general case. But we have slightly, when we look at the Lami system, at least in our, if you think about our fluid structure problem in the container, we actually have two different sets of boundary operators depending on which boundary we are at. So we have our fluid structure interface, where we have one system of boundary operators, and on the outer boundary we have another system of boundary operators. So what we are actually looking at in our case is a system which looks like this. So we have an omega. We have an omega. Think of omega as our container with a fluid and elastic walls. And then we have two disjoint boundaries, gamma 1 and gamma 2. And on gamma 1, we have one system of boundary operators, and gamma 2, we have another system. So we're looking at this type of problems. Now, Aquin-Douglas-Nuremberg, as I said, essentially relies on a localization argument. So it's absolutely no problem to generalize the Aquin-Douglas-Nuremberg stuff to this setting here. And so this I just put into the slides here, the generalization of Aquin-Douglas-Nuremberg. Then, of course, when you have two systems of boundary operators, you have to construct your setting of function spaces accordingly. And but still, all the statements of the Aquin-Douglas-Nuremberg theorem, they still hold. And yeah, let's leave it at that. Okay, so so today I want to talk about the Lami system. I want to show using this tool set that the Lami system is elliptic in the sense of Aquin-Douglas-Nuremberg. Okay, that's one thing. Furthermore, I will show that it is Fredholm of index 0, and then I will show that the kernel is trivial, so that we end up with a homeomorphism. And because of the Gamuna theorem, we get homeomorphism in any LP setting, although I will actually work with the Hilbert space case. That's the beauty of the Gamuna theorem. Okay, so what is the Lami system? The Lami system is the linearization of our non-linear system of different partial differential equations that we use to model elastic material. We consider here now a bounded domain. Okay, I work primarily in R3, of course, with two boundaries, as in our cylinder, not cylinder, as in our container with the elastic walls, disjoint boundaries. I introduce the symmetric part of the gradient of u, I call it d of u, and then I just linearize my the nonlinear Stammer-Kirchhoff elasticity equations, and you end up with the so-called Lami system. Okay, still not super simple, but also not super hard to write. So we have the divergence of the first Lami constant, lambda e, of well, the trace of du times the identity matrix plus 2 times the second Lami constant times du. So the divergence of this must be equal to the outer force, and then we have, of course, the well, the expression without the divergence, the tensor in the divergence expression, times n is equal to g1 on the gamma 1 boundary, and u is equal to g2 on the second part of the boundary. So we have a mixed Neumann Dirichlet boundary condition, Neumann boundary condition in the sense with respect to the corresponding stress tensor here. Okay, so that's the Lami system, and we need to show that this system in the setting of LP Sobolev spaces is a homeomorphism. Okay, so first we compute the partial differential equation in our system, the field equation, and so this is actually not so. This is actually a nice operator. At the end of the day, you can express it as a constant times Laplace u plus a constant times grad of dvu. So the Laplacian, by the way, the Laplacian obviously is the divergence of grad. So it's a divergence of grad u plus a constant times divergence grad u plus constant time gradient divergence u. So there's some symmetry there. So it's not all bad. The Lami system can be expressed. Okay, now I computed just the symbols of the operator. Okay, so this is boring stuff. I just take the differential operator and compute the symbols, right? So did this for the A, and I've done this also for the boundary. Of course, the boundary symbols depend on the normal direction. So what I did is I computed for the three for the three canonical directions, the boundary symbols, and then of course I get in the general case just a linear combination of my boundary symbols. And okay, so in the canonical directions, in the unit directions of our three-dimensional space, we get these symbols here, so they are nice, and we can. So this is the symbols corresponding to the Neumann boundary condition, and of course the symbol corresponding to the Dirichlet boundary condition is even simpler. This is like this. Okay, so from the symbols we can more or less directly find the suitable weights. Okay, so yeah, so I have here weights which satisfy the conditions of the Aquin-Doctor's Nuremberg theorem. You have to find these weights. As I said, the weights confuse me. Not that confuse me as such, but I really have a hard time with these weights that you can choose in a non-unique way. But okay, that's what it is. That's the Aquin-Doctor's Nuremberg theorem. I've chosen the weights here, and looked at the principal parts. You can take here compute the degree of the characteristic polynomial 6, and yeah, okay. So after we have fixed the weights, then we have also, or from the weights, follow the setting of function spaces that we need to use. Now I have, for some reason, I have changed the exponent of our subular spaces from a P to a Q. Of course, I've done this because at some point I need to also look at the Stokes equations, and in the Stokes equations, P is usually used to denote the pressure, so I need a different letter to denote the exponent in my subular spaces. Okay, so this is the framework of function spaces in which we now consider our Lami system. And it's the frame of Sobolev spaces dictated by the Aquin-Doctor's Nuremberg theory. Now the goal is to show that in this function setting of function spaces, our Lami operator is a Fredholm of index 0. I like to show this Fredholm of index 0 because there's a nice theorem that we can use for this purpose. And the theorem enables us, I will tell you the theorem in a moment, the theorem enables us to derive the index of our problem from a simpler problem. Let me just show you how this goes. So what we do is we introduce now an operator here. A naught, B naught 1, B naught 2, which can easily be shown to be Fredholm of index 0 in the Hilbert space case. Then we connect this simple operator to our Lami operator via a path in the space of a bounded operator in our setting of Sobolev spaces. Okay, and then we show that the index is preserved on the path, so that we derive that the Lami operator has also index 0, because, well, the simple operator had index 0, and they are connected on a path on which the index doesn't change. So that's the idea. That's how you reduce the hard work of showing Fredholm of index 0 to a simpler problem. Okay, and the theorem we need for this is the following theorem from functional analysis. When you have two Banach spaces, then a subset of and if you have an open subset of Fredholm operators, so it's a subset in the space of bounded operators from our Banach space X and Y. So obviously my Banach space X is back here. So my Banach space X is in this case V2, 2, and my Banach space Y is the corresponding canonical Banach space for my right-hand side of my problem, so that's why. Okay, so in general, when you have an open subset of Fredholm operators in the space of bounded operators, no, sorry, I have to quote the theorem correctly. I just have to read what the theorem says. So let F, or calligraphic F, I'm talking about the theorem down here, that calligraphic F denote the complete subset, the full subset of Fredholm operators in the space of bounded operators. Then this set is open. So the component of Fredholm operators is an open set. Okay, we know that. More importantly, the index is homotopically stable. That is, the index is invariant along any continuous path in F. And so all we have to do is we have to connect our two operators by a continuous path in the component of Fredholm operators, and then this beautiful theorem says the index doesn't change. So that's how we get index 0. Okay, now let me proceed and show you first here the simple problem where I can show by standard theorem that it's Fredholm of the corresponding operator in the Hilbert space setting is Fredholm of here Hilbert space setting. So now we put p equal to 2, right? So we have here the corresponding Sobolev Hilbert spaces for our data and the corresponding Hilbert space for our solution. In the Hilbert space case, I can show with completely standard PDE method that the Laplace problem you see here, Laplace u equal to f in omega, a normal derivative of m equal to g1 on the gamma 1 and u equal to g2 on gamma 2. So this is a mixed Dirichlet-Neumann boundary problem, but the boundaries gamma 1 and gamma 2 are disjoint. So it's absolutely standard problem. At the end of the day, you can show existence with Lax-Milgram. We have normal elliptic regularity theory to get regularity. Uniqueness by just testing standard stuff. So in the Hilbert space case, really, this mixed Neumann Dirichlet Laplace problem can be treated, and we can show that for any data f g1 and g2 there is a unique solution. We can even show the nice a priori estimate. This means that the operator is a homeomorphism, in fact. So this means, in particular, it's Fredholm of index 0. Okay. Fredholm of index 0. That's the important thing. Okay. So now I want to derive. Now I want to show that my Lami operator is also Fredholm of index 0. As I said before, all we need to do really is connect our Lami operator to the say Laplace operator in the set of Fredholm operators with a continuous path. And this path you see down here. So I use the parameter t. This is not time. This is just the parameter I use for my path. So I connect down here, essentially. I connect the operator AL with the operator A naught. Right, because if I define a path like this, so I get for each t, I get I get an operator. For each t, I get an operator at, bt1 and bt2, right? And when t is equal to 0, this operator is a naught, b naught 1, b2, and when t is equal to 1, this operator is a 1, b. This is my Lami operator with corresponding boundary operators. So I have here just a simple path from my Laplace operator to my Lami operator. So the path has to be, okay, continuous. This is clear in the space of bounded operators. But more importantly, the path has to be in the component of Fredholm operators. So what I have to show now is I have to show that my operator AT, BT1, BT2 is Fredholm for any t. Then I have a path in the Fredholm component, then I know that the index doesn't change, and then I have the wonderful statement that my Lami operator's index 0. Okay, so how do I show that my AT operator is Fredholm? Well, I use the theorem of Gamuna. I show that it's elliptic in the sense of Aquin-Douglas Nuremberg, but because this means Fredholm. So I check that that it's properly elliptic. Okay, I do this here. Take the principal symbol of my AT operator, compute the determinant of the characteristic polynomial, and of course I have to here compute quite a lot. But at the end of the day, I can compute and get a nice result, which clearly gives me a determinant, a characteristic polynomial, which is negative everywhere. Okay, so this means my operator is A, T is properly elliptic. Now we need to verify the complementing boundary condition. To this end, we employ the Lopachinski-Shapiro condition. So I consider now my AT operator in a half space. So here we have the half space. Yeah, I fix some psi, which is tangent to the half space, and n naught here is the normal component to the half space. Okay, and then I consider my problem, the AT problem in the half space, and the Lopachinski-Shapiro condition or the theorem says that if I have a solution of this type here, where the function b decays exponentially, then if I can show that any solution to my half space problem on this form, if I can show that this is trivial, then I have no non-trivial solutions of this form, and then I know that the complementing condition is satisfied. So now we have to show that this u here of this form, which we assume is a solution to the half space problem, that this u is 0. Okay, so this I do by integration. So I don't want to integrate of the whole of the half space. So I fix first some cube, a cube, right? So this is a cube which is part of my half space. Okay, so basically, if I show for each such cube that my function is 0 on the cube, and then I know it's 0 everywhere, and then I'm done. Okay, so yeah, okay, so this is okay, this is a little bit, I don't think I have, there must be a little mistake here because is this really a cube? So I have the normal, I have the tangent, and I have the other tangent direction. So psi is just some vector in the tangent space, and then I have the two tangent directions, and I have the normal, and then So, but they should be normal. Why do I say P? I need there's some normalization missing here. But anyhow, that's not. So this is confusing me. So I have. No, I take just the cube. Sorry, I'm talking to myself now. Okay, so Q is a cube in my half space. Okay. Now I just do normal energy method stuff here. I multiply my dot multiply the solution with the equations and integrate over a cube. So now I have constructed the cube so that my solution here is periodic in the tangential directions, right? So due to the oscillating factor here of periodicity in the tangential directions in my cube, so that makes it easy to change to make an integration by parts. So that's why I fix this type of cube here. Okay, but essentially the argument, I mean, it's not, it's just, it's a classical stuff. I have my equations here for my, this is the AT of the right-hand side of AT U equals to 0. I dot multiply the right-hand side of my equation with the U. I know that that I have 0, and then, but I integrate over Q, so look what I get. Okay. Divergence here, obviously, I do integration by parts, so the divergence after integration by parts, I get a gradient of U. Here, this is scalar product of matrices, so it's just integration by parts, and I don't get any boundary terms due to the periodicity in the tangential direction. So what about the normal directions? Yeah, in the normal direction, of course, I have a solution to my problem. So I know due to the boundary, I have a solution to the homogeneous problem in the half space. So I know, so I also have the boundary conditions here on the half space. So this is on one face of my cubes. I have my I have my boundary conditions, and I have periodicity on the other faces of my cube. So this is not a cube, this is an infinite sector. No, it can't be. It has to be a cube. Okay, I'm a little bit worried about this. Well, not worried because it's a standard argument, but when we do this this integration by parts, there is one face of the cube that should produce boundary values, but it's not an issue because I can because I go because the V here is decaying exponentially. So yeah, no, it's not. It's not a cube. Of course, when I look here, it's just it's an infinite rectangle. This is Q. Oh, now I'm getting have problems with my pen here. Anyway, so it's an infinite rectangle, and I can integrate by parts because I have exponential decay in the infinite direction. Okay, so let's not get hung up in the details here. The point is, I verify I'm verifying the Lopachinski-Shapiro condition by assuming I have a solution to my half space problem of the type oscillation term times exponential decaying term. Then I dot multiply the equations, the half space equations with the solution, and I integrate by parts. So I have, of course, my 0. And after integration by parts, the point is, after integration by parts, I have only terms that are not negative here. Okay, so but this means that all the terms are 0. In particular, the symmetric part of my gradient u is 0. And the divergence of u is also 0. Okay, but this means that well, when the symmetric part of u is 0, that means that u looks like this. It's a rigid motion, right? But due to the decay and the periodicity of the u, I mean, we're assuming u has a certain form, it cannot be a non-trivial rigid motion, and so u is 0. So let's just leave it at that. The idea behind that argument. Now, so we are verifying here the Lobachevsky-Shapiro condition. This means that at any point on our path, so any operator, actually, here is the full operator, right? This is the operator at the point T on our path. So along our path, we have only Fredholm operators, right? Because we have here shown that the operator is satisfies Erkman-Douglas Nuremberg condition, so it's Fredholm. So I have a path now in the component of Fredholm operator. So I have a path in the Fredholm component of bounded operators from x to y. Okay, so due to the theorem I showed you before, the index remains unchanged on this path. So the 0 index of the simple Laplacian problem remains, this 0 index remains for my Lami problem. So my Lami operator has index 0. So now it's a small step for me to show that the Lami operator is in fact a homeomorphism in the Hilbert space case. Okay. So the x and the y spaces, they are the Hilbert space case, p equal to 2. In this case, I can use my solution as a testing function, right? So I can, again, I can look at solution in the kernel and dot multiplying the corresponding equations with the solution itself, integrating by parts. I get, and this is the same integration as before, I get that divergence of u and the symmetric part of the gradient of u are 0. Again, the same argument, then u is a rigid motion, but I know that I have a solution which is also 0 on the outer boundary. This rules out that I have a non-trivial rigid motion. So in fact, I have a trivial rigid motion. I have u equal to 0. So what I show here is that the kernel of my Lami operator, kernel of the Lami operator is, let me just take this over here. The kernel of the Lami operator is trivial. Okay, I know that my Lami operator in the Hilbert space setting is Fredholm of index 0. I know that the kernel of my operator in this Hilbert space setting is trivial. So in the Hilbert space setting, it is a homeomorphism. But the theorem of Gamuna tells me that the theorem of Gamuna tells me, sorry, that wasn't my last slide. The theorem of Gamuna tells me that not only is the Fredholm index independent of the p. Sorry, actually, now I want to go back. So if you allow me, because this is the last slide, so I can find my way back here very, very quickly. But I like just this theorem of Gamuna that I'm using. This is, here it is. So I know that my Lami operator in the case q equals to 2 is Fredholm. of index 0. So the Gamuna theorem here says that then I have then the operator is Fredholm for any LQ in any LQ setting, and the index and the kernel are independent of Q. This is also important. So I know that the kernel is trivial when Q is equal to 2. Yeah, but then the kernel is trivial for any LQ in any LQ setting. And also the index is independent of the Q. I know that the index is 0 in the Hilbert space case, so the index is 0 in the LP case. So there's a theorem of Gamuna in combination, which relies on the Aquin-Doctor's Nuremberg theorem here, gives me this nice and very in general very complicated step to go from the Hilbert space case to the LP space in this elliptic setting here. So in fact, and now I go back to my last slide, in fact, I get that my Lami operator is a homeomorphism in any in a general LQ Sobolev space setting. You can choose any Q between 1 and infinity, and you get that the Lami operator is a homeomorphism in the corresponding setting of Sobolev spaces. So, okay, so that was my goal with the talk today, to show this. Next week, I will show, and this is very easy now because this is the hard part in the fluid structure interaction, in the steady state fluid structure interaction problem, to show that well, both systems, Stokes and Lami, are act as homeomorphism in such a Sobolev LQ setting. Now I've shown it here only for the Lami system. The Stokes system, I can rely on textbook material. It's not easy, I know, but I'm not going to spend a lot of time doing that. I can give you references that the Stokes system is also a homeomorphism. Probably you know even from lectures at Waseda that this is the case. And then I have two homeomorphisms in the LP Sobolev setting. In this case, the fluid structure coupling is reduces to a relative simple fixed point type argument, and then I get a solution to the steady state system. Now, to be honest, I didn't. I don't know if I finished. No, I didn't have any breaks, so that's why I'm a little bit early. But finishing early. So I wanted to show you this next week, and then next week we go the next step to the unsteady case. I like the time periodic case as the first unsteady fluid structure problem after the steady state case. So I will talk about this next week, and yeah. So this was what I prepared for you today. In summary, we derived the equations of motion. I told you about the basic physical principles upon which the equations of motion are derived for the elasticity equations. The Samolov-Kirchhoff material in particular. We touched upon the Stokes, the Navier-Stokes system, as well as how they were derived. And then we looked at the steady state coupled fluid structure system. I showed that the Lami operator, which is the linearization of the nonlinear 3D elasticity equations, that the Lami operator is a homeomorphism in a general Sobolev space setting using the Aquin-Doctor's Nuremberg theorem. The same holds for the Stokes operator. Next week, I will show existence then of a solution to the steady state solution. This is just a very quick argument, and then we move on to the unsteady case. Okay, so ladies and gentlemen, thank you very much for your attention.
Thank you, Matt. Very interesting. So, do you have any questions? Comment? Thank you, Matt. But For example, stationary program test is the domains are already given, or you also decided domain is stationary program.
The domains are unknown.
Today you talk about the linear program, so it's okay. But if you consider the nonlinear program, but still for the stationary program, then the domain is given, or even you decide domain.
So here's the stationary problem.
Yes, so the omega is container is a given, but then
so we have
fluid part and the elastic part is also given for migration.
So the reference configuration, so omega
is a given, of course. It is a container is a given. Yes, it's okay. But then you have two domain. One is elastic domain.
Omega. So the omega, the current configuration of the fluid. This is the complement. So let's say we have a bounded a box. So let's say we have here the bounded box, and then here. So the full domain, let's call it a B.
Yeah. Okay. So the stationary program is the domains are given. I see.
Well, no, because the current configuration, this is the complement. So this is what is outside of the current configuration.
Yes, this okay.
The elastic body. So let me just write it like this: CE cur, right? Yes. But the current configuration, the reference configuration is given, but the current configuration is not given. So this is this is the deformed reference configuration.
Yes.
But the phi isn't unknown. So in fact, the phi
I see.
This is u plus the identity.
Yes.
Of omega e ref. So in fact, the current configuration up here, this one depends on u.
Okay. Okay, so now I catch you, but also the time-dependent program. Also, time-dependent program, the equation for the elasticity is on the fixed domain, but
so here's the time-dependent program.
Yes. This is also the u is defined on the fixed domain omega sub e of 0.
Yes. So this is, of course, this is known.
Yes. But then
this is unknown.
Yes, but okay. So then the phi is defined by identity plus u. Then once you define the u, then you can define the omega e of t, right?
Yeah, exactly.
But then what you have to prove is that omega e sub t is the b minus omega ft or something like that. It's defined by omega e0, yes. But then this is equal to the container minus omega f sub t.
Yes.
You have to prove, or this is automatically satisfied, or I don't touch this one.
Okay, so
omega, yes, omega sub et is defined by u. Yes, I understood. Then finally, you have to prove that omega sub e,
yes,
and the omega sub f is equal to the containers. Right? Yes.
In fact, you have to show that.
You have to show this.
That yes, but this so the thing is that we only get in the elliptic case we get existence for small data. So we are looking at small solutions, and for small solutions,
yeah, of course, no. Yeah,
you're right. This is part of the. This also has to be shown that the that we don't have any degeneration of the geometry.
I see. Okay. Yeah, it's very quite interesting for your formulations.
But you're absolutely right that today I focus on the linear part. The linear part is the difficult part to get the LP theory.
Yes.
Now, today I wanted to show this argument for the Lami system, because I could not, when I was studying this problem first time many years ago, I could not find the LP theory for the Lami system. So this was, it said, but there is Aquin Nuremberg. So it's Aquin Nuremberg, and just one line, all the papers said, but no book or anywhere did anybody show that in fact it was in fact it was elliptic fragment of Nuremberg. So I just wanted to show this how to do this. It's not a surprise in any way, but it's quite a lot of work to when you do this rigorously.
Okay. So I usually use the ZD, sorry, not the Gmonad. Yeah, I also studied Douglas Nuremberg when I was young. I mean, 20 years old days. So 40 years old.
Could you name?
Years old I studied, but then later I prefer to use the ZD theorem. But that case I have to show.
How do you spell that? How do you spell that, sir?
CD, SEELEY.
The Sealy, yeah.
Yeah, it's a little bit different to Gemini, but the Sealy case is you put lambda first. I mean, lambda plus or minus Lami equation. You solve it. So that's the lambda is large enough, then you can solve, because even in LP.
But then that's like the resolvent problem corresponding.
Yes. And then you consider the bounded domain. Therefore, lambda equals 0 is not in resolvent. Lambda belongs to the resolvent.
Yes, of course. Yeah, sure. Actually, I learned this trick from you last time I was in Waseda.
Yeah. Yes.
That's true. That's actually a nice way to do it. Yeah.
It is, the idea is ZD, not Gmonad, but it's okay.
Yeah.
It is so for me it's okay. But I don't know. Maybe your lecture is very good for the young peoples, because now nobody talk about the Aquin Nuremberg.
This I think is a problem that you. I mean, when you work with elliptic systems, you have to use, because also the series is also from the 70s, right?
Yes. It
is something I know the paper. So this, for elliptic systems, it's, in many books, it just says, elliptic in the sense of Aquin Nuremberg. You can look in the paper, and therefore you get these nice estimates. But in fact, the Aquin Nuremberg paper don't give you the full homeomorphism property. They just give you the estimates, the local estimates a priori.
Yes. Yes, you are right. I think the existence theorem is independent of the
Exactly. So the system is independent. And so how do you go from just knowing that your system is elliptic in the sense of Aquin Nuremberg to showing that there's a unique solution, and this satisfies also the full estimate without the lower order terms on the right-hand side?
Yeah.
So the Aquin Nuremberg paper is only part of the full story.
Just estimate only, yeah.
Just the estimate.
Yes.
But you have to use something like,
as far as I know, that even, for example, Professor Solonikov, so he showed only the estimate. Then the existence theorem is maybe people believe that a priori, a priori estimate implies that existence. But from my point of view, ZD is show this one.
Yes, I agree. I agree completely. So Sealy is but you have to use either Sealy or or the Gamuna, or
Yes,
you have to
also
go put into, you have
Yeah.
to put a little more effort. And you know, the book that everybody cites
Yeah.
on elasticity is the
Charest.
book.
Charest, yeah. Yes.
So, and in CLA, he does not, I mean, he uses the whole book, LP theory, right? So he relies on what I showed today, that the Lami operator is has these wonderful LP properties. In fact, that it's a homeomorphism inverted. And he just says, okay, but it's he never shows it. He just says, look in the paper back in Dr. Nuremberg. So that was my motivation for doing this proof.
I see. Sure. Yeah, as far as I understood, when I was young, also I studied the Marsden Hugh. Maybe CRA is, I have also only a lecture note, very thin lecture note.
Yes.
So maybe Marsden Hugh.
Yeah, Marsden and Hughes, exactly.
Yeah,
it's
good, very big books concerning the elasticity.
Yeah.
But in this book also talk about the physics, but no mathematics. Mathematical part is
there's no mathematics. I think
they talk about the mathematics, but I don't satisfy their mathematics. Maybe share also. So you are right, I guess. So
also the book of I have that book also, Marsden and Hughes. But also here you don't find the full LP stuff.
No.
Maybe they mention it like CLA.
Yeah, sure.
By the way, now that I mentioned this, there is one funny thing. Now that we talk about Aquin Douglas Nuremberg.
Yeah. Okay. Very good. Yeah, it's very nice. I think very nice. I think. But also the time-dependent program. You talk about LP theory for the elastic part, as far as I'm. But is it true? Because when I was young, I also studied that the elastic, the hyperbolic equation is well posed only in L2, not LP.
Yeah, it's not. You don't get the full LP.
But you have some dissipation or something like that. I don't know. But
there is a dissipation, but only when you couple the elasticity with the fluid. Then the fluid.
Yeah, fluid part.
Boundary condition. This is a dissipation.
Yes.
So, but it's not clear because normally when you look at elasticity equations, right? So you have dt or some let's say plate equations, right? So you have Piola plus. Oh, I can't write. Sorry. So normally, if you put some dt Laplace u term.
Yes.
I don't know why it's making this. So no. So when you can put these damping terms into your hyperbolic operator, and then you have sort of regularized it. But of course, those terms that you sometimes put in, they are not physically well. They are. One also want to show theorems without these sort of sometimes artificial damping terms, right?
No, I don't think so. It is a very famous equation for the viscoelastic, was it?
Yeah, for viscoelastic. Yeah, sure. But then you have the viscoelastic part. But if you want just the pure plate or pure 3D elasticity, then these damping terms are not justified, I think.
Yeah, but if you drop these terms, then you really get the hyperbolic equation.
Yes, then you are in full hyperbolic.
You can solve only the L2, I guess.
Yes, but there is so if you have I can't if you have your hyperbolic equation, then when you couple your hyperbolic equation with the fluid equation, so you couple it with your parabolic equation, then in fact the boundary condition acts as the boundary term from the fluid. So the boundary force from the fluid, this term actually is a dissipation term.
Yes, I believe it. Yeah.
So it acts like dt Laplace u. So it regularizes.
Oh,
So this opens up for some LP theory. But the problem is that it's not clear precisely how this dissipation is manifested. So it's from a physical point of view, it's clear that that when you have the structure coupled with the fluid, then energy from the structure goes into the fluid, and in the fluid the energy is dissipated. So as a full system, you have dissipation, but it's via the fluid. So so for the fully coupled system, so if you look at the hyperbolic fluid plate equation on its own, there's no way you can get LP for anything other than P equal 2.
Yeah, P equal 2, yes. Okay.
But if you couple with the fluid equation, so you have you have to very linearize very precisely, then you get a coupled system which has some LP properties. That I will talk about next week.
Okay, good. That's quite curious. Yes,
but can I say just one anecdote, which I think is a little bit funny? The Aquin Douglas Nuremberg.
Yeah.
Do you know the book? What is? You know, there is some famous books on Navier Stokes. What is, so we have like the book of Galdi, and then there's a book, what is the French guy called? You know, I forget his name. Who wrote a book also before Galdi? What was his name?
Okay. Maybe I forgot the name, but famous guy.
Yes.
I
now I forget his name. Right?
Yeah.
Anyway, so in this book, better I don't mention the name, he shows that the Stokes system is elliptic in the sense of Aquin Douglas Nuremberg. So he serves this complementing condition here. But he shows the complementing condition directly. So he looks at these polynomials, right? But in the paper of Aquin Douglas Nuremberg, they don't say cofactor matrix. They say adjoint matrix.
Yeah.
Because in old days, back in the 50s, the adjoint matrix, this was the cofactor matrix.
I see.
But nowadays, most people, when you say adjoint matrix, you think of the complex transpose.
Well, yeah, sure. Okay. I see.
So in this famous book, when he shows that the Stokes operator is elliptic in the sense of Aquin Douglas Nuremberg, he's using the wrong matrix. So he's using not the cofactor.
Okay, because he forget the divergence condition, no? Maybe because of the pressure, or in compressible cases, I agree completely, but incompressible cases, we have a pressure term, right?
Yes.
Therefore, I don't believe the Stokes system becomes Aquin Douglas Nuremberg.
No, there's
okay.
The Stokes is no, but in the unsteady case you have the problem.
Okay. I see. Okay.
So it's not, because this was what Solonnikov was trying for so many years, right? To show that the Stokes, to find some notion of ellipticity that carries over to the parabolic case.
Yes.
But for Stokes system, this is due to the pressure. It's apparently not really elliptic. So that's probably, you cannot use Sealy for Stokes, I guess.
No, I don't think so. The Solonnikov also, they derived the very nice a priori estimate, I guess, for the non-slip condition case. But from this, you cannot derive the Aquin Douglas Nuremberg. I mean, Stokes. Incompressible case. Stokes is Aquin Douglas Nuremberg system. You cannot say this one. Okay, no, I'm not so.
By the way, I was in Lund last week to give a talk in Sweden. And I met Gerd Grupp, and I said I would be meeting you this week, and she said, please give me your greetings. You know Gerd Grupp? She remembers you.
No, no. Very, some lady mathematician. Very
Yes, a lady
welcome
from
with Hermanda.
exactly. Yes, she's
So
an
yes,
old elderly woman. She worked a lot with Hermanda.
yes. I don't even. But she also worked together with Solonikov, right?
Yes, with Solonikov and Hermanda.
Hermanda. Grad.
Krop, yes.
Right, something like that. I met her in St. Petersburg once. Yeah, sure.
Yeah. No, that's really nice. She because she worked a lot with Solonikov on
Yes.
Hermanda, and she knew a lot of great stories about them.
She has a.
Did you ever meet Hermanda?
Sorry?
Did you ever meet Lars Hermanda?
When I was 27 years old, I participated in one meeting, and then Hermanda was the one of the boss of these meetings. Yes, only once. Only once. More than 40 years ago.
Yeah.
So,
Yeah.
yeah, 40 years ago. Yes. In Italy.
Oh.
Yeah, sure. I studied Hermanda's book, but a very old book, not new.
Yeah, me too. It's quite complicated though. I
Yes,
think it's
yes.
difficult to read.
Oh, it's a very nice chapter with you, but
Yes.
anyways,
Oh, yes.
it's I very enjoyed. But I'm sorry that maybe we should stop because
We should stop all the yeah. You're right. So I
maybe
hope
I'm very pity I cannot meet you because of the COVID.
Yeah, this COVID is horrible. And
okay, so I'm looking forward to hearing you again the next week. Yeah,
next week,
the
same time, I guess, right?
Okay, so thank you so much. You were very nice.
Oh, thank you, and see you next week.
Yeah, see you next week. Thank you. So bye bye. Ciao.